This will be our last lesson on thermodynamics. Remember, we're covering both thermochem and thermodynamics with Big Idea 5. And we'll get into the latter part of it toward the end. But you want to be able to use the laws of thermodynamics to describe the essential role of energy. And we already talked about the first and the third law of thermodynamics. Remember, with the first law, the change in internal energy is equal to the heat plus the work. We talked about the third law of thermo, where we said the entropy of a perfect crystal at 0 degrees is 0 because atomic and molecular motion ceases to exist. And then finally, the second law of thermodynamics talks about entropy change of the universe, and you can calculate total entropy or the entropy of the universe in regard to the sum of the entropy of the system and the surroundings. Any entropy lost by the system is gained by the surroundings, and vice versa. The second law of thermo says that all thermodynamically favorable processes will increase entropy of the universe, and you will see that an increase in entropy helps generate thermodynamically favorable reactions. However, when you're considering thermodynamic favorability or spontaneity, you're not only considering entropy, you're also considering enthalpy. And that's what we're going to look at here. This is based on the system. You're going to hold temperature and pressure constant, and you can calculate delta G, the change in free energy, the change in Gibbs free energy, named for Gibbs. And I had a student who was up at Yale, and this was right after he was accepted. He went to do a tour of Yale, and I get this text of a statue, and I'm trying to read the inscription at the bottom, and I guess Gibbs went to Yale because there was a big statue of him, and he's like, oh, this is the coolest thing. I think the campus actually was a lot prettier, but he thought it was neat, so he sent it to me. No, this is a long time ago. In fact, he just finished college, and I'm sure he's making easily $200,000 a year. And I think actually he went into business, if I'm not mistaken. But don't you worry, he took his AP credits and ran. Delta G is equal to delta H, the change in enthalpy, minus T delta S. The change in free energy determines whether a reaction is thermodynamically favorable, also known as spontaneous or exergonic. Thermodynamically favorable reactions have delta G's less than 0. If the reaction is not thermodynamically favorable, delta G will be positive or greater than 0, and if the reaction's at chemical equilibrium, where the rate of the forward and the rate of the reverse reactions are equal, delta G will be 0. And just to put some of this in perspective, because it can get very tricky, delta G is the change in Gibbs free energy when it's negative, the reaction is going to be thermodynamically favorable. When it's positive, the reaction will be thermodynamically unfavorable. Delta H is the change in enthalpy. A negative value is indicative of exo or endothermic. Exothermic. Endothermic. And then delta S is the change in entropy when negative versus positive, which one signifies disorder. Negative is correct. Remember, no, no, no. Negative order, disorder.
And it's more thermodynamic. I can't speak.
It's more thermodynamically favorable what?
If it's order.
No. Disorder favors thermodynamic favorability, but you have to consider enthalpy as well, and that's what we'll look at here.
Do we calculate enthalpy, or is it usually?
You know how to calculate enthalpy already. You can do it from the delta H's of formation. You know how to calculate entropy already from the table, as we talked about the other day, always products minus reactants. Remember, the only time you do reactants minus products is for bond energy. The other thing, and I think what some of you may be thinking if you worked on this last year, delta G is equal to delta H minus T delta S.
Are we going to have problems like that on the test?
Uh-huh. In order to be thermodynamically favorable, delta G has to be negative. I'm going to put a little smiley there. An exothermic reaction that favors disorder with a positive delta S will always generate a thermodynamically favorable reaction, because a negative minus a positive will be a negative delta G value, thermodynamically favorable. And again, you can memorize if you want, but it's much easier to do this piece mathematically, I think. In contrast, an endothermic reaction that favors order will never yield a thermodynamically favorable reaction. Questions so far? And this is why exothermic reactions tend to be thermodynamically favorable. Disordered reactions tend to be thermodynamically favorable, but you have to consider the combination. You could have an exothermic reaction favoring order. When will that type of exothermic reaction favoring order be thermodynamically favorable? The temperature would be low, correct? Because then if the temperature is low, this term doesn't have much of an effect. It is the delta H term that predominates. So at low temperature, the delta H term predominates. And again, exothermic reactions tend to be thermodynamically favorable. In contrast,
Was that said before the T?
low,
Before that?
at low temperature. Little sloppy. You want it fixed? Or you got it?
Dr. English?
Yep.
On the notes, I know the special characters don't show up, but what's the formula for delta H of formation? Because right now it's a coliseum and a train.
The delta H is products minus reactants, but
No,
what?
delta S, sorry.
It's also products minus reactants. What might look very funny is that it's like a script V, and that's indicative of stoichiometric coefficients. So from the other
It says
day,
Coliseum.
are you looking here?
Yeah.
Yes.
Oh, it's a sigma and then a
So sum of taking into account the stoichiometric coefficients, products versus reactants.
So for down Coliseum is train.
Okay, so you just multiply the coefficient times the delta
Yeah,
H.
just like we did the
delta
other day.
S.
Just
Okay.
make sure the train doesn't leave the building not knowing anything. All right.
So that's sum. Train is sum.
Now at high temperature,
Oh, it's like that.
which term's going to predominate? Delta S. So now you have a negative minus a very large negative term, and that will give rise to a thermodynamically unfavorable reaction. So at low temperature, delta H predominates. At high temperature, delta S predominates. Uh-huh.
On the notes on this, there's like two formulas for delta G.
Right, we're going to hit that.
What's the second one?
Hang on.
Okay.
You're way ahead of me.
Oh, okay.
That's okay. So basically, what I did mathematically is all written there. But I'm not one to memorize. I like to interpret. I think it's easier, and especially if you're nervous, you're less apt to make a careless error. Where we're going with this, where you're going with this, I believe is here. We're not quite there, and I'll
no,
answer.
It was up above the.
Oh,
That second one.
what?
Never mind.
It's just what she just did.
It's,
Yeah,
yeah, it's this formula.
no.
I just plugged values in.
Yeah.
Yeah, that's what I think was confusing. Okay, so if we look at the examples shown here, it says predict whether the reaction is likely to be thermodynamically favorable at high temperature. We're given a delta H, endo or exo? Exo. Is this reaction favoring order or disorder?
Disorder.
Why is it order?
I was just looking at the first one.
See, and this, and I'm not going to scold you, but this one time, if you do not look over what we did the previous time, it is difficult to understand what we do this time. College course moves very quickly. I want you to do well, but you have got to stay up to speed with what we're doing. That means reviewing what we did last time.
I was just looking at the first line and I saw negative. So
Tell me why it's order.
Because the products are less than the reactants, so if you subtract two, you get a negative answer.
You have any values there? What do you mean you subtract? What are you subtracting?
Is it because the difference in the two delta H's is positive?
Nope. Has nothing to do with entropy.
Does that do with what type of like reaction?
Nope. Maybe slightly, actually. Slightly in this case. But not always. So what are you really looking at in that balanced equation?
Coefficients?
Coefficients? What does that tell you?
The coefficient, so the coefficient of the product is 1, the coefficient of the combined reactants is 3, so 1 minus 3 is -2. So because it's negative, it's order.
Almost. You're getting there. Not only do you look at the coefficients, you also look at the state of
Oh,
matter.
matter.
So in this case, your trick is going to work, but in an explanation, you're not quite there. You're more there than what anyone else provided. What you're looking at here is you have all gases in that reaction. How many moles of gaseous reactant do you have?
3.
3. How many moles of gaseous product do you have? 1. So what you have here is the moles of gaseous product, which is 1, is less than the moles of gaseous reactant, which is 3. And so the reaction illustrates order. You want to indicate the moles of gaseous reactant versus moles of gaseous product. Joe, in answering your question, we ultimately are going to be calculating the delta N exactly like you did, 1 minus 3. But your explanation's not quite where it needs to be. It's almost there. So just be specific in the moles of gaseous product versus reactant. This goes back to what I said the other day. You want to babysit 3 kids or 1 kid? 1, because it's more orderly. But in chemistry, we want disorder. So we're going from 3 moles of gaseous reactant to 1 mole of gaseous product. So in this instance, we're going toward order. Is delta S positive or negative? Negative is correct. So what you've got here, and you can show the equation and explain your interpretation, you've got a negative. They're telling you the temperature is high, but we're going toward order. So you have exothermic, but you've got order. A negative minus a huge negative will give rise to a positive delta G, and this will be thermodynamically unfavorable. In the second example, same approach. They're saying high temperature, you have an endothermic reaction. Explain to me why this reaction illustrates disorder.
If the coefficient of the products out to 2 and the products of, or the sum of the reactants is 1. So when you subtract it, it is a positive answer, and it's still got they're both gaseous states.
You're almost there because you threw gaseous in. So I think you just about got it. You saved it with the gaseous. I was like, and then the gaseous came up. Yeah, you've got 2 moles of gaseous product being generated from 1 mole of gaseous reactant, and that's indicative of disorder. With disorder, is delta S positive or negative?
Negative. Oh, wait, sorry, positive.
Positive. Remember, no, 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 no. You want to take the car out and stay out till 4 in the morning? No. Negative order. This is disorder. Positive. You've got a positive minus a bigger positive will give rise to a negative delta G. Thermodynamically favorable?
Yes.
Yes, yes, yes. Pretty easy conceptual interpretation with the equation. Much easier with practice. As we've said before, and we've drawn it out diagrammatically, here is just some indications of things we've talked about. Typically, decomp reactions are endothermic, synthesis are exo. Combustions are always exo. When you make bonds, you are synthesizing, exothermic. When you break bonds, endothermic. Freezing and condensing are always exo. Melting and boiling are always endo, and we talked about this last time. Dissolving will increase entropy in almost every instance because the ions will be able to move freely. The one time you do see a decrease in entropy is when you form very strong hydration shells where you have ions that are surrounded by water molecules, but they will tell you what the entropy is, so you won't have to predict. They'll tell you and they'll ask you why, and that's in the instance of the hydration shells that we drew previously where you have the ion in the middle and the 4 or 6 water molecules surrounding them. We're going to calculate standard free energy change. This is delta G naught. The naught indicates that gases are at 1 atmosphere of pressure and the temperature at which the experiment's being run is 25 degrees Celsius. You can calculate delta G as delta H minus T delta S, and it says here make sure the units are the same.
It's not on it.
Oops. Sign. Whoopsie. Thank you. Make sure the units are the same. The same, the same. What you're really going to need to watch, the temperature needs to be in Kelvin. The delta S that we calculated the other day is either in joules per Kelvin or joules per mole Kelvin. And you're going to need to convert that to kilojoules per Kelvin. Otherwise, you're not going to have the same units when you subtract through. Be very careful there. That is the common mistake that kids make. Now, Andrew, I thought this was your question, because delta G can be calculated two different ways. You can do products minus reactants, as we've done previously, where the delta G values would be given. Delta G for any free element in its standard state or any diatomic element in its standard state, the delta G of formation is 0. So delta G values can be provided, and you do it just like we did delta H or delta S. No difference there. Products minus reactants, or more than likely you'll be using this formula. Let's walk through this first example together. It says use the Gibbs equation and standard free energies of formation to calculate the standard free energy change at 25 degrees Celsius for the following. So the equations given, these values were not provided to you initially. I threw them in. I'm going to change it ever so slightly, only because it doesn't match what's down below, and I don't want you to be confused. It's close. But I did not give you these values. You probably want to scribble them in your notes right now. And then I want to calculate delta G together both ways.
Wait, which values are we writing down?
The ones that are highlighted in gray.
Okay.
Or here's green.
Oh, just like for the example.
Yeah.
What do we do if they're not gases?
You still do it. That's just, you're thinking KEQ, and we'll get there in a few minutes. Unless you're thinking like entropy with solids or liquids, and there you're pretty much looking solid to liquid, increase in entropy, liquid to solid, decrease in entropy.
Ours would be gaseous, and then under that would be aqueous, right?
Oh, wait, can you go back?
We're going to do it. You're going to see it right here. All right. So let's say we want to calculate delta G as delta H minus T delta S. The delta H is given at negative 114.1 kilojoule. Endo or exothermic? Exo. Temperature is 298 Kelvin. Delta S is a problem. The delta S they gave us is negative 146.2 joules per Kelvin. But we need kilojoules per Kelvin, so what do? You divide by 1,000, or move the decimal 3 to the left is correct. Be careful. That's a careless error you don't want to make. We have negative 114.1 minus 298 times negative 0.1462. And they gave it to me at 25 degrees Celsius. That's 2 sig figs. I'm going to give that back. Although if you did 3, it wouldn't matter. Let's go with 2 answers here. Negative 70.5 kilojoules, or we'll do negative 70. Initially it was 0.53 and change, so we'll go negative 71 kilojoules. Either one's fine. Is that thermodynamically favorable? Why?
Since delta G is negative.
You got it.
So the only thing you want to be positive is delta S.
Uh-huh. And I put the not signs there. They were given as such. I just didn't copy the formula as such.
The what signs?
That's a not sign. That means standard conditions, 1 atmosphere of pressure for gases and
I thought that just
25
meant
degrees. No, not there. Degrees before like degrees Celsius, and there is no degree before Kelvin. No degree before Kelvin. You can also calculate delta G of a reaction doing products minus reactants, taking into account number of moles of each. So 2 moles of nitrogen dioxide times its delta G of formation minus 2 moles of nitrogen monoxide times its delta G of formation plus 1 mole of oxygen times its delta G of formation, which is 0. And when you do it this way, you get negative 69.7 kilojoules. And actually, probably should be 7.0 because maintaining decimals there. And those are grossly similar. So you can calculate delta G 2 ways, although if I were going to guess, I think they'd ask you for it this way. Or instead of calculating it, they might indicate the reaction's thermodynamically favorable and exothermic. You know, at low temperature, delta S would have to be what? Or, you know, something along those lines. Or it might say the reaction's exothermic, favoring order. At low temperature, you would predict the reaction is thermodynamically favorable. There's another problem here. This one is far more involved. We're going to keep it a little simpler than what's shown here. If you have this reaction shown here, and let's say all of this not in pink were given, you could calculate the delta G of the reaction either from the delta G's of formation, or you could get the delta H and delta S of the reaction and then calculate delta G. What temperature is 25 degrees Celsius. So what I want you to do is try and get delta G using this formula. The delta H is here. The delta S is here. See if you can get delta G that way. The products minus reactants I'm not worried about. You already know how to do it. Watch your units. Watch, 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 watch units. And I got exactly what's shown there. Now, if you didn't get it, look at my work, look at yours, see if anything isn't quite meshing.
Why is it two sig figs?
You know, the sig fig thing, keep in mind when you're adding or subtracting, you're going to the least number of decimal places, so I'll usually match it up that way.
I got 6.470, so is that 6.4?
6.5.
Okay.
Even number followed by a 7 rounds up. Any number followed by a 7 rounds up. All right, but again, if a mistake's going to be made, it's going to be made right here. Don't forget, in order to subtract, you must have the same units. I am 63 inches. You are 70 inches. You are 7 inches taller than I. When you add or subtract, you must have the same units. The last couple things we want to look at today is linking Gibbs free energy to equilibrium. Equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. We have said here delta G is positive. Would that be thermodynamically favorable or thermodynamically unfavorable? Unfavorable. So a positive value is unfavorable, a negative value for delta G is favorable. At equilibrium, delta G is 0. So if you have that same formula we talked about, delta G is equal to delta H minus T delta S, at equilibrium delta G is 0. So you could set these two equal to one another. And one thing you can do is you can relate enthalpy and entropy when a substance undergoes a phase change. And that's something they have done. They've calculated the delta S for vaporization for many different substances. And they say it's usually about 87 joules per mole Kelvin. And this has come to be known as Troughton's rule. I don't really think it's anything you're going to need to know. I'm not going to worry about it. And again, if you knew you were at equilibrium, you could easily manipulate this formula to calculate any of those variables. At equilibrium, delta G is 0. What we really want to do is look at the relationship between delta G under standard conditions and the equilibrium constant, KEQ. Now, equilibrium constant is new to many of you. It is not difficult. I'm going to show you how to write it in this chapter, but you won't be responsible for writing it until the next chapter. However, that variable is in a formula that links to delta G. That you'll be responsible for now. When you have an equilibrium situation between liquid water and water vapor at 100 degrees Celsius, you know that these two molecules transition back and forth, and we know that water boils at 373 Kelvin or 100 degrees Celsius. If you consider vaporization of water at a lower temperature, you will find that vaporization occurs, but many more molecules will be in the liquid as opposed to the gaseous state. This is not thermodynamically favorable with a positive delta G. And what you've got here is, although this reaction is reversible, the reverse reaction is more favored than the forward reaction, hence the positive delta G. Now, at equilibrium, delta G under standard conditions will be 0. Non-standard conditions, that is different temperatures and different pressures, delta G will be 0, not delta G naught. And what you can do is you can write an equation, and all of these are given to you on your formula sheet. When you consider what you're given, pretty rich in the Thermo unit, you've got all of these product minus reactant formulas. You've got your delta G is equal to delta H minus T delta S, so they give that to you. They also give you delta G naught is equal to negative R, universal gas constant, times the temperature, ln of K, and that's KEQ. So delta G would be 0 in this case. Delta G naught would be what you're solving for. The R is provided right here, and you'll recognize it because it's got joules as one of its derived units there. So if we replace delta G with 0, then we've got this. Solving for it, I just showed you, watch the R, the temperature's in Kelvin, and the only other piece is that delta G naught has to be in joules because R is in joules per mole Kelvin. So you got to get those joules to cancel. They give you this formula highlighted in yellow. They don't give you the formula highlighted in blue, but you can derive it. Essentially, you're going after this piece. So you've got delta G over negative RT, and then to get rid of the ln, I learned it as antilog. You, I know, have learned it as e to the whatever power. So you can just solve it that way. And we're going to solve for this in just a minute. For those of you unfamiliar with KEQ, it's really easy. When you write an equilibrium constant, let's say you have this generic formula here, this genetic, not formula, chemical equation. KEQ, product concentrations raised to their stoichiometric coefficients, the product of over the product of the reactant concentrations raised to their stoichiometric coefficients. Only gases and aqueous entities, no solids, no liquids. You'll see more of that in the next chapter. I won't ask you to write KEQ at this stage. You'll get it in the next chapter. I just wanted you to show you what KEQ expressions look like. Here's an example. Write the KEQ expression for the following. Products on top. Just remember pot. Products on top. You've got aluminum ion. I was thinking of the pot you cook in, but okay.
Yeah,
Aluminum ion raised to the stoichiometric coefficient of 2. Hydrogen gas raised to the coefficient of 3. Note these substances are added. In a KEQ expression, it is the product of the concentration you are multiplying. Over reactant. Why didn't I include aluminum? It's a solid. And then proton. Do I put the 6 here?
No.
You better not. The 6 becomes the exponent. This was the equation I had given you previously. You could calculate KEQ off of it. I guess we could do that one. Let's take a look. We want to know the value for KEQ. KEQ is equal to E negative G over RT. Delta G here is given in kilojoules. I'm going to keep that negative sign in the formula. The delta G is positive. I need joules. I'm going to move the decimal 3 to the right. R is 8.314 joules Kelvin times the temperature is 298 Kelvin. Kelvin cancels. I've got negative 8,590 divided by 8.314 times 298. That needs to be in parentheses equal. And then I'm going to hit second EX, second answer, and go. Wow, that looks kind of funny. What'd you guys get? My graphing calculator's charging in the back. What'd you get? What'd you get?
No one did, except for you.
Why not?
Because I'm having trouble with my calculator.
What'd you get? What'd you get?
3.
That's what I got. It just looks funny. Usually you don't get things like that. But the delta G is pretty small, so that actually does make sense. Yeah, that's what I got. So 0.031, no unit for KEQ, or 3.1 times 10 to the negative 2. With this delta G, is the reaction thermodynamically favorable? The delta G is 8.590. Thermodynamically favorable? No. Thermodynamically unfavorable reactions have KEQ values less than 1. So that's going to be a negative exponent, which is what you got there. Now, with that said, let's see if you can do this problem. You want to figure out KEQ. First, you have to get the delta G. Here's the KEQ. See if you get it. Give it a shot.
Would they give you the KEQ?
No, that's the answer. Don't peek.
Oh.
Just disappear.
Determine the KEQ using this.
First, you have to get the delta G of the reaction. Give it a shot. Go, go, go.
How do you know when to put the not and when to not put the not?
Standard conditions, 25 degrees Celsius.
So you put it on this one?
Yep.
Wait, is it spelled not like N-A-U-G-H-T?
Yeah, like naughty without the Y.
Yeah.
It's not, it's not. And that may be a bad New York accent showing
You know
through.
what?
Don't make fun.
It's
My
not
mom
not,
always
it's
comes
not.
out whenever
Hey,
she says-
naughties, let's go!
Naughty.
You're so silly.
Whenever my mom says coffee.
Hey, focus! What's your delta G? You're lagging
Coffee.
behind.
I know that.
Killer.
Wait, but all the products are zeros.
So you don't have, so then what's your delta G?
Negative,
No.
I mean positive 1.
Your delta G is positive 117 kilojoules. Now see if you can go after KEQ. Here's what I got, and here's my work.
That was the same thing that was written in pink.
Why is negative?
To tell you the truth, I think there should have been 4 Siggy Wiggies on there, and it doesn't really matter, but
That's okay, why is it negative?
why is what negative? This, I think, maybe should have been 0.1. And then you would have kept the 1 here. But it doesn't make a difference. I don't want to make a mess. I think it's easier to just leave it. I'll take either answer. Just making a big mess.
Dr. K, who's your favorite? Or
Come on, let's focus. Another thing I want to point out, thermodynamically favorable? No, no, no. KEQ, negative exponent. And that you'll see in the next chapter. When you've got positive values of delta G, the reaction's not thermodynamically favorable, and if it has a large positive quantity, essentially no reaction's going to occur. So if you're like huge, 10 to the 10th power, the reaction's not going to go.
Like animals.
Nah, too many obstacles. Right, and I think that's what I was driving at. I think I was a little lazy with my sig figs. Probably should have maintained the 4 sig figs there. So if you did that, you would have had 117,100 divided by 8.314 times 298 close equals second close equals, actually I didn't get it that, oh I forgot the negative sign, idiot. Negative 117,100 divided by 8.314 times 298 close, boom, 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 boom.
Is that what you said when you did it?
Yeah, so if this is this, and everything else is the same, I do get 2.98 times 10 to the negative 21. It doesn't matter. It's all the same. Don't worry about it. So you can calculate KEQ, and again, I just want to make it clear that this formula is given. Delta G is equal to negative RT ln of K, but you have to be able to derive KEQ is equal to E to the negative delta G over RT. That should not be an issue with your math level. I already mentioned in regard to the values. The last thing I want to mention, two things. The dependence of delta G and KEQ on temperature is no longer assessed on the AP exam, so we're not going to bother with it. I did put this line in this morning. I don't really think this has been assessed in the last few years, but it is listed as one of the objectives. I have a short little movie clip. It's about 4 to 5 minutes. This is one of the Bozeman videos, and some of you have not watched Bozeman videos the whole year, which has been a tremendous disservice to you. They are extremely helpful, and they really illustrate concepts well. There are a lot of Bozeman videos here. I mean, they're all here. I've got a link on your Edline page, but there's a lot in the Thermo unit. So if you have any concepts that really aren't clear, hit them, because it'll really help. But the one I'm going to show now is 60, because this is how you, he's going to show you coupled reactions, how you couple reactions together so you can drive non-spontaneous processes or thermodynamically unfavorable processes. So I'm going to show you this video. I apologize, the sound system in here is poor and the video is going to pop. So we'll try and watch it if we can't really get the point across. You can watch it at home or maybe watch it off the Chromebooks. It might actually be preferable. But this is going to link everything together now in regard to using those laws of thermodynamics to describe the essential roles of energy here and predict the direction of changes in matter. Is it thermodynamically favorable or not? And these videos are very good. If you haven't watched them, please spend the time.
Hi, it's Mr. Anderson, and this is Chemistry Essentials, video 60. It's on driving non-spontaneous processes. And those are processes that don't occur without external energy. We also call them thermodynamically non-favorable. Sometimes we call them endergonic. But if we were to look at a free energy diagram like that, we're essentially looking at an uphill reaction where we have a positive delta G. we shove on it, it's just going to return to where it was before. And so how do we lift that? In other words, how do we lift that when the reactants actually have less free energy than the products do? Well, there's two ways that we can do that. First of all, we could add energy from the outside. So this is just a model, but if we add energy from the outside, then we can lift those reactants and eventually have the energy of the products. Where's that energy coming from? It could externally come from electricity. For example, we're charging a rechargeable battery, or it might even come from the sun. And so that's how a solar panel works, or how a leaf works if we're looking at photosynthesis. Another way we can do it is we can couple it to a spontaneous process. And so if we were to look at an exergonic or an energy releasing process like this, where our delta G is less than 0, that's going to be a downhill reaction. So you could imagine if we were to couple those two together, and again, this is just a model, then we could take some of that energy released in that spontaneous reaction and use it in a non-spontaneous reaction. So again, in a non-spontaneous process, our delta G is a positive value. So our goal is to make it a negative value. In other words, make this spontaneous. We can do that in one of two ways. We can take energy in from the surroundings. So for example, if we use electricity, like when we're charging a battery, then we can change that delta G to a negative value. Likewise, if we were to take in light, for example, in photosynthesis, we can turn that upside down as well. We can also couple it to another reaction or to another process. So for example, in our body, we constantly do this using a molecule called ATP. Every time we convert ATP into ADP, we release a little bit of energy, and we use that to do things like think and move and talk. And so let's start with the electricity. So if we're looking at a battery like this, why does the battery eventually run out? It's because our reactants have more energy than our products do. And so we're losing that energy. Now we're using that to do work, we're using it and losing it as thermal energy, but eventually you have a battery that doesn't work. And so how am I going to recharge it? I have to connect it to electricity. And what that electricity can do is it can actually turn those products into reactants and then add energy to them, and we can recharge that battery so we can use it over and over again. Likewise, if we look at life on our planet, most of us are heterotrophs. What does that mean? We take energy in our food. So we take energy in our food, for example, like glucose, we combine it with oxygen, we make carbon dioxide and water. But when we do that, the reactants, in other words, our food and our oxygen, have a higher amount of free energy than the products that we produce. And so we would be stuck if it weren't for the autotrophs, if it weren't for plants. What they can do is turn that backwards. In other words, they can take that carbon dioxide and water, and they can add energy to it. Now, where are they getting the energy from? They're getting it from the sun. And so how does photosynthesis work? Well, inside a leaf, you have chloroplasts, and inside the chloroplast, you have a membrane like this. And what it's doing is it's taking in energy from the light. What's it doing with that energy? It's getting its electrons excited. It's passing those electrons down an electron transport chain, and eventually those high energy electrons go back into your food. Now, who are they making that food for? Themselves, because they're going to do that same process in respiration. Now, whereas a lot of that energy goes to this molecule, where does it go? A lot of that energy goes to this molecule right here, ATP, which is used in energy coupling inside our body. And so again, we're using external energy to turn that endergonic reaction upside down. Now that's one of only two ways that we can do this. We can also energy couple. And so what's going on there? We're taking an endergonic reaction and coupling it to an exergonic reaction, or we're pairing a non-spontaneous with a spontaneous reaction. So inside our body, the molecule that we use over and over and over again is going to be ATP, or adenosine triphosphate. And on the end, it has these 3 phosphate molecules. And as this last phosphate pops off, it releases energy with it. And so that's going to be a spontaneous reaction. It's releasing energy. But then we can break our food down. And as we do that, that releases energy, which we can use non-spontaneously to create more ATP. And it's said that you go through your whole body weight in ATP every day. Now, what do we use that ATP to do? We use it to couple to non-spontaneous reactions inside our body. So, for example, how do your nerves work? If we look at the lining of a nerve, or the membrane of a nerve, we have the spontaneous release of the phosphate as we break down ATP, but we're using that for non-spontaneous movement of ions inside and outside. If we're to look at a muscle, what we're doing is that spontaneous release of the phosphate is coupled to a non-spontaneous contraction of that muscle fiber. And so again, it's not like we're using electricity, it's not like we're using light, we're storing energy in molecules, and then we're simply coupling that to exergonic reactions. reactions. So did you learn to explain how external energy and energy coupling can be used to drive endergonic reactions? I hope so, and I hope that was helpful.
And again, I think the videos are very good because they link concepts together. They give you a good conceptual understanding. The one other thing I would say about that video, you're not going to see anything like that for the most part in your textbook. Your textbook is strictly chemistry. But, you know, kids always say, do you like teaching bio or chemistry better, or what do you like better? The answer is neither. I like them when they're put together. So when you get the biochemistry basis, a lot more things make sense. So that's one other thing I really like about that video. So that finishes off your thermochemistry as well as thermodynamics, both chapters 6 and 17. You'll be assessed on the quiz Monday, and we'll do the lab where you will become familiar with calorimetry and design and make hand warmers next time. Questions, anything here?